Thanks. Okay, this is where we stop in the end of the last section. So this is pictorial representations of the energy shell of the classical Bose-Hubbard model. For any case, again, we write the quantum Hamiltonian of the Bose-Hubbard model, where this is creation operator and n is the number operator. If the number of the particles can show, then you can drop this term. It's like simple. And this is the classical Hamiltonian of the Bose-Hubbard model. So if you don't believe me that the classical Hamiltonian looks like this one, then later on I can provide you the rigorous justification of this classical Hamiltonian. But it looks like this, where instead of the microscopic interaction constant, you have the macroscopic interaction constant, which is like the n. Energy surface is some kind of the Hipple sphere. Hipple sphere because of these normalization conditions. And from this Hamiltonian, you have the Hamiltonian equation of motion for the L complex variable. And so we think you find the trajectory in the phase space. So it is relatively easy to find the volume of the energy shell. But the next question is, what is the relative volume of the chaotic and regular component? Then the strategy is quite simple. We simply, again, wrong button. The bottom is too many. The standard procedure. You randomly pick up initial condition, any trajectory on the energy shell, and then evolve the trajectory and do its stability analysis. The stability analysis is, of course, calculate the Lyapunov exponent. This is the equation of the conventional space. This is check you that the initial condition belongs to the energy shell, and then you find the Lyapunov exponent. So the next slide shows the value for the Lyapunov exponent calculated for the classical Bose-Hubbard. So here altogether, a relatively simple sampling of the system, only 1000 initial conditions. So the upper panel is the size of the energy shell. And this is the Lyapunov exponent, which belongs to this energy shell. So you see that you will hardly find zero Lyapunov exponent. It's here zero, you also find zero, but the majority of the trajectories which you tested are chaotic. So then you can claim that the many-body Bose-Hubbard model is almost completely chaotic classical system. Okay. This is lattice Lyapunov exponent. Find the time lattice Lyapunov. Okay. Yes. For the regular, it should be zero. Yes, you simply count the number of the zero Lyapunov exponents. Here, I guess you find 10 points. So 10 points from 1000. This is where I found the regular dynamics. This is justifies this. yes. Oh. Now you should really count the number of the zero level of exponential from zero level. This gives you the ratio of the chaotic and the regular component. Okay, so then we come to the main conditions of the quantum pair, that if you have chaotic complex dynamics, the energy spectrum for the quantum system should obey the universal statistics. So then, easy check. For a small number system, you really calculate the quantum Hamiltonian of the Banach model. First, you fix the basis. So if we work in the Fock basis of the one-year state, then you have to redistribute n particles over L well, all possible ways, and this gives you your Fock space in the basis of the one-year state. Of course, the Hilbert space, the dimension of this Hilbert space grows exponentially both with n and L. But for, let's say, something like 8 particles in 8 well, you can easily calculate it in this laptop. Then you calculate the matrix of this Hamiltonian. It looks like this one, so it is very sparse. Of course, it depends on the ordering of this Fock state, but this is actually nature ordering. You can also change bases, for example, use this canonical transformation. Then the Bose-Hubbard Hamiltonian will look completely different, but it is the same Hamiltonian, and calculate the Hamiltonian in these bases. Then it looks like this one. It's also sparse. Also, this is more sparse than this. I don't know the reason. And then diagonalize it. After you diagonalize it, you do the standard statistics, calculate the normalized distances between levels, and compare with the Wigner-Dyson distribution and Poissonian distributions, which is expected for a given system. So of course, it is easy to compare not distribution, but integrated distribution, like this one. Numerically, it is easier. And here is the results. For some small systems with constant U, the same like J, and the mean field factor NL equal to 8 approximately. Mean field factor 1 particle per 1 side. So you see quite good agreement with the Wigner-Dyson distributions. It even can be taken better by some methods removing regular states, but agreement is quite good. This is results of the 2004. Yes, of course. This is the case when U is of the order of G. These terms are equally important. Yes, you can, of course, if you set U to 0, the system completely integrable. Or if you set J to 0, it's again completely integrable. So in between, you have non-integrability. In the quadratic physics, when we have more or less J and J U, or like this one. Then the transition is when you increase interaction. I will show in the next slides how it looks like. Okay. So interesting is that this also works in the opposite direction. So you have Bose-Hubbard quantum Hamiltonian, calculate the energy spectrum, and then you can say something about the classical Bose-Hubbard model. And this is the example I want to show. This is this one. This is three-side Bose-Hubbard, only three-side. Now it is energy flow when I change the interaction constant J. This one. So considering to the left 20 particles, to the right 40 particles. It is all energy levels of this system for 20 particles as I increase the interactions. So you see that you expect the Wigner-Dyson statistic here. Here it's we expect the Wigner-Dyson statistics here. Then when you do the classical analysis, you find that the energy cells of the classical model with this energy is mostly filled with chaotic trajectories. In fact, this spectrum this paper was devoted to the other topic. As you know, the ground states is always regular states. And we know, according to the Bogoliubov theory, that there are some elementary excitations above the ground states, which call the Bogoliubov excitations. And this is also regular states. And this is to show that this Bogoliubov spectrum. So you see here the spectrum is scaled according to the Bogoliubov frequency. And then if you do this, you should see in the next to the ground states equidistant spectrum. And this is the proof. And in fact, this Bogoliubov frequency can be extracted by usual Sommerfeld quantizations of the invariant toric, which is belong to the lower energy states, lower energies of the classical Bose-Haber model. So this you don't need to introduce the Bogoliubov series. It was introduced by the Bogoliubov. You simply carefully consider the phase space of the classical. Okay, this was about the spectrum and about the eigenstates. Of course, one should say something about the eigenstates. Well, I should admit that I didn't address this properties of the eigenstates from the viewpoint of the eigenstates normalization theory, because it was before this topic became popular. But this is the simplest test. I don't know who is it transducing, but and also do not know why it's called the local density of states. But statement is like this. So if you have the chaotic eigenstates, they should possess sensitivity to the parameters. And this sensitivity is like this. For example, we calculate the all eigenstates of the Hamiltonian for some value of the interaction constant. Then slightly change the interaction constant U. Then this matrix will and then start to deviate from the diagonal one. And this deviation from the diagonal one described by the relation. For two prime, if we do this diagonal matrix, then it starts to be arranged. Where this quantity gamma is proportional difference between 0 and 2 prime. And this is the check of the state. So essentially, this figure shows the cup of this line. We have nice agreement with Lorenz. We have now both the statements that the spectrum is chaotic and I understand they have, we can use it for some particular purposes. For example, one can use the Bose-Haber model as a bus. This is relations to your lecture. Let's consider a stupid model. The wider Laurentian, but it's wider Laurentian. What is happening? I do not know. I know that for small. Oh, here I have this is for many sites. This is for many sites, but I have this is for many sites. It's what we have. We can check together. Simply find the eigenstate. Is this property. How will you find them in this project? This is not the rule, this is matrix with two elements, M and N. And M and N, this is index of the eigenstates of the Bose-Haber Hamiltonian. This one. No, this is prediction of the random matrix theory, and this is a check comparison. So real system with the prediction of the random. Okay, so I consider quite stupid systems from the viewpoint of the laboratory experiment, but which is nice for. So I consider them L size for the model like this one. I excite the far from the ground states where the eigenstate is chaotic. And I attach to the end of the chain two level systems, for example, spin. And consider that there is funny interaction between the systems and what this is now like us, where interaction. By the way, it's written here. Yes, is the interaction creation created first side, second side, and this is a sigma plus which flips the spin. So it looks like this. That if some particles come from this side to this one, flips, spin flips. If particle goes to this one, it's again flips. Of course, this is not so important. I mean, the only reason to do this is that to divide the now composed systems into the system and the bus. System which is now what? Yeah. If you have problems when some system is the bus. So first, of course, the thought. The density matrix of the systems, which is traced over the last variable of the total density matrix. Also introduce the reduced density matrix of the bus, which is traced over the system variable of the total density. The total density matrix, of course, obeys the standard evolution equation, which is this one. E the time is equal to commutator of the many-body Hamiltonian of the composed system. This is plus is the base. Is the base, which is equivalent of the Schrödinger equation. So the whole evolution of the system is Hamiltonian. Sense? Hamiltonian. But my interest only is the system. You can consider the initial conditions, which is, let's say, factorizes but then as soon as you switch on interaction, epsilon is the epsilon somewhere, sure to be epsilon. More constant. As soon as you switch an epsilon, you will observe how the systems get entangled with the reservoir. It's really very interesting, and you can use this model to see this in the real time in your computer. How the system becomes entangled with the reservoir. And the result of this entanglement is the decoherence of the two-level system. Then there is standard procedure how to one derive equation of motion only for the systems of the interest. And it involves one important approximation called Born-Markov approximation. So now you simply say, let's assume that Born-Mar approximation is justified. And then you can derive by using the standard procedure. If you want, you can repeat it. The master equation for the two-level system. Now it is Hamiltonian of the two-level systems, 2 by 2 matrix. And this is some kind of relaxation or lead block activation. And you have explicit form for this relaxation or lead block activation. It's like this one. And the gamma is proportional to epsilon squared. The epsilon is the Cartesian constant. Then it is easy to solve this equation. And solution will be that all diagonal elements of the density matrix exponentially decays, and populations of the upper and lower levels equilibrates. This is solution of this master equation. Now we do really direct test. We solve the whole problem exactly. Then take the trace and check what we see. See? The all diagonal elements decay exponentially. The populations of the level sites equilibrates, which proves that Bazar-Hubbard models in the highly excited state can be considered as a Markovian path. This is, I would say, important application of the quantum chaos. We can use the systems as a mass. If you ask me the question, what this one, this is the measure of the entanglement. Measure of the entanglement is this entropy entanglement. Okay, this was numerical check. What is next? Next are the intermediate conclusions. The many sides Bazar-Hubbard model is generally chaotic systems in the sense of those the classical equation. This is a statement that when you have interactions and hopping, I would say, order, then overwhelming majority of the states are chaotic states. Of course, they are excluded are the low energy states, close to the ground states, and some highly excited states close to the upper boundary of the spectrum, which presumably are localized states, quantum breezes. Then this is just conclusion that if we bring the systems in the chaotic energy states, which is simply excited pretty far from the ground states, it can show as a Markovian bus. I come to the next chapter where address the question how we can detect quantum chaos experimentally. I'm using the cold atoms. Yes, yes, it looks that the 6 atom in 6 wells is not big system. But in fact, what is matter is the dimension of the Hilbert space. And dimension of the Hilbert space of a two-level systems is only 2. And the 6, it is hundreds. So in this sense, this is big system in comparison, big. It is also good bus. I believe. In some sense, yes. But he is really. And this is exactly what is matters, the dimension of the Hilbert space and the ergodic properties. Yes. We say here is about few hundreds. For 6. atoms. For 6 atom in 6 wells, the dimension is 200. Yes, much smaller. Okay. Nothing happened. This will be even this is certainly non-Markovian, but it is even not usual non-Markovian. Let's say in the very lower level, Markovian bus means that you can obtain the master equation for the systems of your interest is the ordinary differential equation. And non-Markovian bus will imply that you can obtain integral differential equation. But if you use the ground states, you cannot do this. This is certainly the system with the ground states of the bus. Okay. So the first experimental check of the quantum case was oscillations. It's quite interesting story about the Bloch oscillations. I guess I should be safe to explain what is Bloch oscillations. They was introduced, I guess, by Zener in Zener, right? Oh, it can be understood by using the pure classical argument. And it's that the energy spectrum of the quantum particle in the periodic potential is the Bloch bands. Let us consider the ground Bloch bands, and then the dispersion relations can be approximated energy as a function of the momentum dt minus j for sine here will be dispersion relation for the ground Bloch band. Or this ground band usually quite well approximated. Associate the momentum of the systems with the H1 of I/by. And then your classical Hamiltonian in this sense will be look, minus j for sine latest period momentum h. And if you now apply a static force in the solid state physics, it's usually electric force which acts on the electron at this potential Fx. This is potential of the electric field. F is the magnetic field. Now we work the equation of the motion. You have E dot minus the H for H is equal to F. You get the solution. P as expected, accelerated is momentum changes linear in time. The second equation for X it will give you minus j sine and here I should put. Now you plug this solution here, and you will see that X changes periodically, both X and velocity. X dot changes periodically this time. This is a simple classical explanations of the Bloch oscillation. As I said, this phenomenon was predicted in 1934, and then next 50 years or even more, the experimentalists in solid state physics desperately tried to observe this Bloch oscillation. So they succeeded only in 1992, when the people in Dresden Technical University, observed 1.5 Bloch oscillations of electron in the superconductor lattices. Not much, 1.5. The reason is that the solid state physics is very dirty. You have some impurities, you have interaction of the photons, this phonon system, and so on, so on. So, but quite soon, I think it was 1994, as I guess, but quite soon, something like 4 years. This was one. So the solar, there was experiment by the Solomon group with the representations of the Bloch oscillations is called atoms. Few periods, and this is, I mean, sometimes expected because lattices, optical lattices are perfect. There is no impurities. There are no interactions with the phonon system. They are rigid. So then you immediately observe really, let's say, 10 or 12 Bloch oscillations. But then everything starts to accelerate very rapidly. Then quite soon, the experimenters reported observations of the hundreds of the Bloch oscillations and then the thousands of the Bloch oscillations. And this gives some progress also in the precision measurement. If you know the period of the Bloch oscillations, you can derive the period of the Bloch oscillation here. What I can do. So the frequency of Bloch oscillation is defined only magnitude force, like period. So the period 2p divided by L. So if you have 1,000 of the Bloch oscillations, you very well know the frequency, and then very well know the F. And they use it, for example, now for precision measurement of the gravitational force. So now I explain how usually it's done with physics of small particles. So now you, for example, use a static force, gravitational force. It means that now the coordinate x is z coordinate, this one. So gravitational forces are, this is one-dimensional lattices. And then you also have running beam so that you can trap the cloud of your cold atom in some fine region, something like this. Then at time equals 0, we need to switch off dipole trap. So atoms want to fall down, but because of the phenomena of the Bloch oscillations, which can be also treated as the Bragg reflections, so they are then pushed back up and oscillate. It's very precise period of oscillation. As measuring their stuff, they were able to detect change of the gravitational force when you bring close to your setup some mass of the like 200 grams. So just imagine the precision. Compare 200 grams with the mass of the Earth. And still these setups, these Bloch oscillations allows us to detect the change in the period of the Bloch oscillations and the local change of the gravitation force. So really, I mean, the experiments is called atoms I'm using. Okay, but this was about single particle quantum mechanics, or let's say, which is really the same for the ensemble of the atoms, but non-interacting. Of course, we are interested in the case which are directions. And so now the new Hamiltonian is like this one, where I should have this one due to the gravitational force and study it. Now, using quite a simple unitary transformation, you can evaluate the problems in terms of this Hamiltonian, which is now time dependent. We can move this term here as an oscillating phase. It is now oscillating phase. Okay. And next slide shows you again the energy flow for a very small, systems, where now the control parameter is this phase set. It changes within time. So this was for set equal 0, and then how each levels evolve. This is the case of non-interacting atoms. If you start with the ground state, then in percentile you move along the yellow curve, and after one block period, come again back to your initial states. Now you switch on interactions. Crossings between energy levels, which are based with the Dyson statistics. And now when you move here, you unavoidably meet some avoided crossings, and due to round out channeling, you populate a lot of the states in the middle of the spectrum. And this causes the decoherence of the block oscillation. But of course, this is just hand-waving argument. If you want to analyze this problem rigorously, you should study the spectrum of unitary evolution operator, how we call it, before U is already used. Okay. Which is defined as the time order exponent of the And we can analyze block oscillation in terms of locator, you should really study. If you can, for example, construct it numerically, study also the statistics. It will be the same, like shock you are going to sample. But of course, the problem is more complicated because TV depends on F, and you can find also interesting different regime of the block oscillation. For example, when the oscillations become stabilized, this is the case of the strong F. A simple argument why strong F stabilized. The mathematical one argument that in this limit this becomes approaches the diagonal matrix. The wave-hanging argument is the strong Q. You move not slowly but very rapidly, and instead of the diabatic transition of this avoided process, we have diabatic transition. The other simple argument is how that strong periodic driving can stabilize the system with the inverted pendulum. You know, if you invert the pendulum, it is unstable. But if you now shake it, so it stabilizes in the unstable states. Some kind of the argument one we can. Then one theoretical can predict two types of block oscillation. For big driving large block period, it will be exponentially decaying block oscillation. For strong driving, it will be decaying block oscillations with revivals. So then this paper was published in 2003, and 10 years later, Hans-Christoph Megger decided to check these predictions in the laboratory experiment, and this is his results. This is again time of flight images taken from different times, and you want to check the dependence and indeed observe the decay and revival of the block oscillations. Then, of course, in this case, we switch to the case of the deep driving, this is the blue curve, and observe the exponential decay of the block oscillation. So one of the proof of the presence of the quantum chaos in the Hubbard model. maybe one remark. Bose-Hubbard may serve as a bus, and if you couple it with a system, then for the reduced density matrix of the systems, you can obtain the master equation. In this case, you have quite a funny case when the Bose-Hubbard models is a bus for itself. And then you can also derive the master equation, now not for the reduced density matrix, but the single particle density matrix of the particles which are subject to the static force. It predicts the difference of mass. Okay, anyway, so just read the title, interaction use quantum phase device and evidence central condition through quantum chaotic regime in 1D atomic block acceleration. Okay, of course I should mention the other laboratory inference by using which you can also test the quantum phase in the Bose-Hubbard model. This experiment is done in the group by a report in the unit. And he is doing the following. So he has one-dimensional lattices, which can be filled with atoms. Then he used a highly focused electronic beam, which is focused on the one well of the optical potential. This electronic beam ionizes the atoms, and if you put static electric field, you remove the atoms. And the ion goes in one direction, so the electron goes in one direction, but anyway, so it removes the atoms from this level, this one way. And you can count the number of the atoms of the removed from the lower. Then this way you may completely deplete the central well, but if the electronic intensity of the electronic beam is not very big, then you have two processes. The one is depletion of the wells due to the electronic beam, and then you have the refill dynamics because the atoms from the nearby wells can tunnel to the same well. And that is pretty clear that this, so the depletion and the refilling should depend on the initial states of the system. So you can use the ground states, as it was done in the experiment that I said before, but you can apply, let's say, Bloch oscillation for 2 periods, like enough, or for a few periods to bring the system in the completely chaotic states, and then repeat the same experiment. Unfortunately, his setup does not allow to do this, so this is still in the program. So the depletion dynamic. This way, you also can compare the case when you have the ground states and excited states. Regular and chaotic states. Okay, maybe against about the theoretical descriptions, I need this equation because I will use it later on. So now we have the open systems. Now the number of the atoms is not conserved. They are removed from the system. And then you have to describe your system not in terms of the wave function, but in terms of the density matrix. This is the important point. Density matrix is essentially there are blocks which are associated with different number of the atoms. So now the problem from the numerical viewpoint becomes even more harder because you should not consider just Hamiltonian with only, let's say, fixed number of atoms, 10. You also should add the Hamiltonian with 9, 8, 5, 1 atoms. So your total Hamiltonian becomes essentially larger. This is the first point, and then of course, but if you construct this Hamiltonian, which is very somehow is direct sum of the Hamiltonian with the fixed, that it has block structure with Hamiltonian. If this is the blocks with n equal 10 atoms, then comes block with n. and so on. Actually, this is now your Hamiltonian, let's say, in the extended Hilbert space. The density matrix is defined in this Hilbert space, and this is somehow Hamiltonian evolutions of the density matrix. And the fact that you have these losses shows the atoms is described with Lindblad operator, and this is its explicit form. Delta functions means that you focus your beam exactly in the middle of your chain. Okay, as I say, so it depends crucially on the ground state of the system, or if it's a chaotic state. So we study this case theoretically, and of course calculate the depletion dynamics, simple populations of the waves, but I going the detail of this theoretical paper, but better the intermediate conclusions and then come to the next. Okay, this is what you should keep or what should be left after my lectures. This intermediate conclusion. So the Bloch oscillation is a powerful tool to manipulate the many basic quantum states of both atoms in optical lattices. Again, for the case when the interaction constant is the same or there is a hopping constant, a few Bloch period is enough to bring the systems in the chaotic states where it can serve as a Markovian bus. If the number of atoms is not constant, one can to describe the system in terms of the density matrix, function. And in the next chapter, I'm going to consider the so-called boundary-driven open Bazet-Hubbard model, which, from the viewpoint of the traditional solid-state system, is, I just write the most important implementation of many particles. But then it is cautious to perhaps the most important implementation. All right, now I come to this, to the boundary-driven open Bazet-Hubbard model. Okay, this is the setup which we can do. We have Bazet-Hubbard chain with finite number of the dots or sides. So here L, capital L is 1, 2, 3, 4. It is capital L. In this Bazet-Hubbard. And then I attach to the left and the right sides of the systems, the Markovian reservoirs, or let's say reservoir of the bosonic particles. And this is the Markovian classes. They are characterized by a single parameter that is the mean particle density in the reservoir. And we should intuitively expect that if, for example, the mean particle density in this reservoir is larger than this one, you will have a current of the particle from the left to the right. This is the problem for the conductivity, which is fully ground in the solid-state systems. And of course, there are many papers and many authors to study the systems of this one. Contribution by Thomas Kolovsky, people from Ljubljana, which is some review. Sandra Wilberger, who will come here later on. Okay, this is setup. Remarkably, this setup can be realized with cold atoms as well. Now I show you that figure which I borrowed from the experiment of the group Sesslinger, where he studied the conductivity with cold, in his case, fermionic atoms. So what is red? This is essentially the, again, equipotential surface. Atoms are there inside, behind this surface. This you have your left reservoir, this you have the right reservoir. There you're coupled by, let's say, narrow tube. But then she put some very focused laser beams to make kind of the level. Five side was connected to two particle reservoir. She has a different to check the theory of the Landau Picker theory from the solid state physics with respect to the cold atom. Who knows what is the Landau Picker theory? It doesn't matter for the moment. But then, it is just a conductivity. Measure is the current of the Fermi atoms from here to here. I want the current of the base atoms from the left to the right. Okay. Now one should derive master equation for this problem. Again, here we close eyes, okay, and assume the strong periodic property of the bus and use the Bohr and Markov. In fact, this is two approximation, Bohr and Markov, but usually they are working like Bohr and Markov. One can derive the master equation for base atoms in the base-Hubbard chain. So here is the Hamiltonian of the base-Hubbard chain. Again, in the extended states, that is one. And then comes two relaxation operator, as we call, which are responsible for the particles in the reservoir. It has the same thing. Some constant gamma, the mean particle density in the reservoir, and then creation and proliferation operator is the index 1, because this is refers to the left reservoir. Then there is also a term which differs from this one, and also here this one. And there, I mean, this taken together are responsible for the particle exchange between the chain and the reservoir. Particles can go from the reservoir to the base-Hubbard chain, but of course they can go from the base-Hubbard chain back to the reservoir. What this term describes. And of course you have this, for this term you have a similar expression, but here index L should be substituted by the right reservoir, and instead of the subindex 1, you have the subindex L end of the chain. This is your So this is the model, and this is the standard, what is now called the standard open base-Hubbard model. Okay, again, just to show the same that we have. But they have a Hamiltonian reservoir, one reservoir. Yeah. They exchange with the particles using this stuff to use their Markov approximation and get this equation, master equation for the equation should be said that for the reduced density matrix of the atoms in the chain. We trace out all degrees of freedom related to the reservoir. Okay. The nice thing of this model is that it can be solved, at least in the some limit. For example, in the limit of the non-interacting atoms. To calculate the current, it is sufficient to know the single particle density matrix. This I can show you how. Maybe I put the main equation here. So you have now base-Hubbard Hamiltonian. It's now a second. Then you construct the H in the standard space, as I say, which consists of the block, 0 particles, 1 particles in the system, 2 particles in the system, and so on. It goes to infinity. But of course, in the numerical simulations, we truncate it somewhere. This is to check that your numerical results are correct. You simply truncate it at different positions and can check that you don't change anything. Okay, this is now will be your Hamiltonian, Hamiltonian, and you have the equation for the density matrix. This Hamiltonian. And then these two relaxations. I also put here, the both relaxations, which is Hamiltonian. In fact, the structure of the relaxation operator is fixed by the requirement that the race of the density matrix should be equal to unity. Is the mathematical theorem by the one to fix the structure of the relaxation operator. And if you get some relaxation operator, they always have to have this kind of. Only that L is the particle density in the it will be removed by them. As I say, it can be solved analytically. Why? But this is the case of the non-indirected particles. So the only things what you have to know is the single particle density matrix, which is defined by this one. This is L by capital L matrix. Matrix defined this. One can easily calculate it in computer. And if you know it, you are. So first of all, so you can start with very conditions. This structure of the master equation ensure you that you relapse to some state. And you are interested in this steady state. And this is a steady state solution for the master equations. For the single particle density matrix and the chain of the length of you can see that you have populations of the main diagonal. except the first and the last side. The application number here will be exactly given by the an L plus an L divided by 2. Mhm. Okay, good question. Shall comment in a second. Okay, then the point is that if there is no interactions, the Hamiltonian is quadratic with respect to the AL and A. The relaxation terms are also quadratic in the A and A dagger. And then you can write the closed equation for the single particle density matrix and so on. And that's when you have non-interactive settings, you have no problems. Simply derive equation from this equation, derive equation for this density matrix, which is this is huge size, 1,000 by 1,000. This is only L by L. As I say here, in between population for this size is NL plus NL divided by 2. That is the. But you see that the current is proportional to the difference in the density of the left and the right. And here is the contraction. So this is the current, the stationary current, the stationary flow of the bosonic atom from the left to the right. And as you notice, there is no dependence on L. It means that here the transport is ballistic. In some sense, this is definition of the ballistic regime. When the current does not depend on the length of the chain. But of course, this is not the general case. As soon as we include interaction, this will be not true. But without interactions, you have this response. Okay, so but stationary solution, as I say, Q is constant. This and this one are slightly different, one kind of applications, and you have few imagery of diagonal elements which are responsible for the current. You ask, for example, what happens if I just deattach the left reservoir, the right reservoir? There is no sink for the particles. If I deattach the reservoir, the sink matrix will be diagonal matrix. This the diagonal elements will be given with the value. That's the right. Then the left reservoir, if there is no right reservoir, simply fill your systems with the same density. Okay. But there are two main problems now, which we are going to discuss, and I am sure that we will discuss it later on. So this two main problem. This is account for the interparticle interactions and just defining the master equations, or what is the same, just defining the particle approximation. This I am going to discuss in the next lecture, and you will see how again the chaos which appears when we make the interaction zero modifies this ballistic transportation. Okay. Yes, of course. Yes. 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 Yes, of course. Sorry, we come to more sophisticated things. I would say that some new directions of the development the quantum chaos. open quantum systems and the problems in the context. Real lesson development.